3, 2, 1. Alright, here we go. Video number 2 in our exciting week of where I am not sleeping and dealing with a child. Of course, that is future me. I'm currently recording this before we are set to go to the hospital to induce the birth of Olivia. But while you're watching this, I'm probably not sleeping and, genuinely trying to live. So, alright, let's get back into it. Okay, so what's the goal for today? So today, in this video, we're going to talk the last section of Chapter 1 of our book before we move over to Section 2, and then jump over to Section 4, and then jump back to Section 2, and then jump into Section 3, and then go to Section 5. Normal stuff. Usual things. Okay. So, alright, what's the goal for this particular video? So we are going to talk about multiplying matrices. Now, right out the gate, let's put it up here and immediately go, oh boy, what's this? Now, let's remind ourselves the natural way of multiplying, or at least sort of the intuitive way of doing multiplication of two matrices, matching up entries and multiplying them. Right, we talked about that when we talked Rn. That sort of natural way of doing it is called the Hadamard product, and now it's not entirely worthless, but it's pretty much worthless. It turns out multiplying matrices, this doozy is the much better way of doing it. And now at first glance it might be, I don't believe you at all, but as we go, you're going to get more and more convinced that this is really cool, and we'll see it's really powerful for solving systems of linear equations. Again, our main goal. Alright, let's unpack what this is saying here. So, in order to multiply two matrices together, you need an n by p matrix and a p by m. So, note, the columns of A and the rows of B need to be the same. However, the rows of A and the columns of B, they can be different. Alright, now when we multiply them, we get a matrix of dimension nm. So note here, you're taking a matrix, multiplying it by a matrix, and producing another one. It's possible that the sets all three things are coming from are different. Right, so you could have 2, 3, 3, 4, and then this would be 2, 4. And now let's look at the multiplication. What does it say to do? Alright, well, the jkth entry of A times B is, alright, lock down the jth row of A, lock down the kth row of B, run down the middle things, so the columns of A and the rows of B, run from 1 to P, add them up after multiplying them. Multiplying two things together and then adding them all up. Where have I seen that before? Alright, well, let's actually write out an example. Okay, so here I have the matrix 1, 2, 3, 4, a 2 by 2, multiplying the matrix 5, 6, 7, 8, 9, 0, which is a 2 by 3. So dimensions of the matrices are lining up. And, hey, what's the 1, 1 entry going to be? Well, it's 21, but how did I compute that? I computed it like this, and how did I do that? Well, it's the 1, 1, so 1 locks, and then we run from 1 to 2 in here, so the 1, 1 entry of A times the 1, 1 entry of B, which is 5, okay, then plus the 1, 2 entry of A, 2, plus the 2, 1 entry of B, 8. And if you really look at that, it's, oh, hey, it's the dot product of the first row of A with the first column of B. Similarly, if we go to the 1, 2 entry, note that, right, this becomes 1, and that becomes 2, and then this runs from 1 to 2. So 1 times 6 plus 2 times 9. Hey, it's the dot product of the first row of A with the second column of B. And if you look at all the other entries, you'll see that pattern as well. Ooh, almost as if matrix multiplication is built off of the dot product of elements, when we saw that the dot product of elements in Rn encodes information about Rn, specifically geometric information. So our definition of multiplying matrices built off of that. Alright, okay. Hopefully the gears are turning. Alright, now, let's quickly note something here. Because of the funky definition, because of the weird way this is set up, A times B can be defined, but it's very possible that B times A isn't. right? So here we see 1, 2, 3 times 5, 6, 7, 8, 9, 0 is defined. However, if I swap the order, we're not going to be having a good time, right? Note if we were trying to follow that dot product of row and column maneuver, here the row has 3 things, here a column only has 2. Can't make that work. All right. So let's make the whole dot product is what matrix multiplication is built out of a bit more precise. So specifically, we need the following notational equipment. Now, there is no standard notation for the rows and columns of a matrix. You think there would be, because, the rows of a matrix are very important, and the columns are they're the key ingredients. And as we see as we go forward, the collection of the columns and the collection of the rows are going to play a massive role in solving systems of linear equations. So you'd think there'd be some standard notation out there, but there really isn't. This is the notation I like. I saw this on Math Stack Exchange once, and I was like, ooh, that's the good stuff. I'm going to use this. I've never seen this in a textbook. So our textbook doesn't use this. When they want to talk about the columns, they're just like, let these things be they come up with just some generic symbols. But I like this notation, and this is what I will consistently use throughout the course whenever we have to talk about the rows and the columns of matrix, which, as you'll see, is something we do frequently. Alright, so equipped with this beautiful new notation, and note, again, I kind of want to stress the way it works. The jth row of A is an element of Rn, right, because if you fix J, then, K can run from 1 to N. I like it because it's like if you look at the jth entry of this element of Rn, you replace the asterisk with J. It's like the placeholder for where K goes. So I like it. Alright, but let's actually explicitly prove now that the jkth entry of A times B is in fact the dot product of J, the dot product of the jth row of A with the kth column of B. And this is a simple unraveling of definitions. Write out what matrix multiplication was defined as, then recognize, oh hey, this is the H entry of AJ, this is the H entry of BK, the kth column of B, the jth row of A. And note that this lines up and makes sense. This is an element of RP, right? Lock down J, then I have access to 1 all the way up to P. This is also an element of RP. Lock down K, and then this can run from 1 to P. So the dot product here is logical. It is allowed to be done because these are elements of RP. Beautiful. All right, so there we go. Matrix multiplication is just dot products in disguise. Specifically, the jkth entry of the product of 2 matrices is the dot product of the jth row of the first matrix with the kth column of the second. Okay. So hopefully what you're noticing here is that order seems to matter in matrix multiplication. And indeed, matrix multiplication is not commutative. A times B is almost never B times A. Sometimes that happens, but usually it doesn't. If you're interested, 2 matrices with the property that A times B is B times A, they're said to commute. And they're out there. People have studied them. We're not going to get too sweaty about it. But yeah, so as we noted right off the bat, A times B can be defined, and B times A may not be defined. But even if it is, there's no hope of them usually being equal. Sometimes you get lucky. Most of the time you don't.
Look at this.
Oh, that's pretty cool, Charlie. Charlie, I'm still recording this video. Can you let me finish?
But it's kind of like a birthday cake.
Oh, it's a birthday? I got a Play-Doh birthday cake. That's pretty cool.
I put this kind of like circles on it.
Yeah, I see that. That looks pretty cool. It kind of looks like a fish.
And that's a cherry. And I got 2 users if you want to cut it.
Okay.
And I got the knife if you cut it.
Hey, can I finish and then we'll do this?
Okay.
Okay. All right. Just give me a few more minutes, okay?
Okay, but I'll make it cool, okay?
Oh, okay. Sounds good. All right. Cool. All right. There's guest appearance by Charlie. All right. All right. So, okay. So where were we? Matrix multiplication is not commutative. That's one of the many quirks that it has. There are other ones that it has. And this one is probably the worst. That's the second worst. The next one we'll talk about is the worst. So, you can take non-zero matrices, multiply them up, and get the zero matrix. And here's just the hard evidence. Just multiply that out, you'll get that this is 0. So if I tell you that the matrix A times the matrix B is equal to the 0 matrix, you can't tell me shit about A or B, usually. Right? The thing you would want. Right? So right off the bat, two things that you're very used to about multiplication. That it's commutative and that multiplying two things and getting 0 means that one of them is 0. Out the window. Not true at all. And it gets even worse. Let's say I told you the matrix A times the matrix B is equal to the matrix A times the matrix C. B is equal to C, right? Nope. Cancellation is not possible as well. Even if I know A times B is equal to B times, if A times B is equal to A times C. I can't tell you anything about B or C. No hope of them being the same, right? Note if cancellation was possible here, then you would get 3 is equal to pi, which, yeah, how about no on that one? All right. Now, that being said, even though I've just disparaged matrix multiplication, it does behave like multiplication in a lot of other ways. So, multiplying by 0 gets you 0. Multiplying negatives gets rid of the negatives. It has an identity. Multiplying by the identity matrix, it does nothing. Hence its name. Pretty cool. And hey, look, multiplication distributes over addition. Nice. So, even though there are some things that it doesn't do, like commutativity or non-zero things multiplying to non-zero things, or being able to cancel stuff, it still behaves pretty well, as you can see here. And we're not going to go through all the proofs here. I've got all the details of all these proofs typed up, so check that out. But we're going to go ahead and prove them. And you may not be noticing it, but hopefully your brain is noticing that something's missing from this list. Some nice property. I don't have commutativity. I've got distributivity. Ooh, there's another tivity that's missing. More on that in a little bit. But let's prove one. And here's the proof of one. Right, so note here, like many of these other lists that we've seen before of here are things that are working. When we really look at the proof, it's very just index management, right? What is the jkth entry of this? Okay, well, it's the jth row of A, dot product with the kth column of B, plus C. That's what that's equal to. This pulls apart to this. This is equal to A times B, and this is equal to C times A times C. And that's it. Right, a similar thing for the other equality that we claimed. So these proofs are not particularly enlightening, but again, as we've already seen, they do matter. They are worthwhile to take the time to prove, because the fact that I can distribute multiplication across an addition, that's very good that I can do that for matrix multiplication and matrix summation. Right, I'm good thing I can do this. Right, as we've kind of already seen, taking the time to establish these basic algebraic facts, even if the proofs are just, index management or just, minding how symbols look, they're worthwhile. All right. So, speaking of that, there's a tivity missing. Right. So, matrix multiplication fails to be commutative. It is distributive. Could it possibly fail to be associative? Well, that'd be really bad. And in fact, matrix multiplication probably wouldn't have the ubiquitousness that it does if it wasn't associative. So it turns out it is. And it turns out that proving that matrix multiplication is associative takes a little bit of work, very surprisingly. You would think that like the one that's like the oft forgotten one when it comes to mathematical operations. So as we've discussed, right, associativity you kind of take for granted, right? Because you don't really think about it, because you're like, oh, 2 plus 3 plus 5. You're just, oh, I can do that. Well, you're allowed to do that because of associativity, right? Associativity gives that value. And, we would love to do A times B times C and have that make sense. But without associativity, we don't know that. Now, here's the fun thing about matrix multiplication and proving its associativity. Our textbook relegates it to an appendix. It says, yeah, go to the appendix, you want to see a proof of this. And the proof of it is a nightmare. If you think some of the proofs we've done are like index hell, check out what our book does to prove it, matrix multiplication's associativity, because it is, whoa, there are some indexes, let me tell you. Whew. And for the longest time, I myself never actually sat down and proved the associativity of matrix multiplication until I had to teach this class, and I really had to think about it. And I was shocked to discover that, man, nobody seemed to have like really written a proof that like a human being could read. Like our textbook has it in the appendix if you care, but you know it's not easy to get through. So I was shocked at like, wow, why is the proof of the associativity of matrix multiplication so difficult? And I did some Googling, as you do. I looked through my many linear algebra textbooks, and I was so shocked that like no book was ever proving it. They were just like, oh yeah, you can prove this, but not actually proving it. And that's always that always scares me when I find that, where I'm like, oh, wait, it doesn't seem like anybody's actually like took the time to write a proof that's pretty reasonable. So that gets scary, where it's like, oh wait, is this not true, but everybody just thinks it is, because it's like, oh, of course it is. Well, it turns out that matrix multiplication is associative, and you can prove it, but you gotta, and you can do a proof that's very slick, that we're about to perform. But it turns out you gotta introduce some other machinery in order to get it, and it's machinery that we're gonna need when solving systems of linear equation. Isn't that convenient? So, let's talk about that. Alright, so first things first, you may have noticed that, and maybe your brain did, Rn and the set of n by 1 matrices, these aren't different, right? Think about this. This is n rows, 1 column. Hey, isn't that how we write these? Yeah. So it turns out that you can basically just pretend these are the same thing. So if I take an m by n matrix, I can multiply it by a element of Rn accordingly. So a times x is an element of Rn, and if you write out what it's equal to that. So yeah, you can take a matrix and multiply it by an element of Rn and get an element of Rn out of it. Alright, so as we go into solving systems linear equations, which I promise we will formally get into when we get into chapter 2 next week, it turns out that they can be built off of a matrix times a vector. So we want to look at this, and side note, we're going to be able to prove matrix multiplication associative using this. Alright, now this will become very useful and very powerful, but it turns out to really ensure that that happens, we have to introduce another set of very powerful and important things, the standard basis elements of Rn. Now these are the elements of Rn defined as follows. The jth element's kth entry is 1 if j and k are equal, and 0 if they're not. And if you're going, hey, wait a minute, isn't that the identity matrix? Oh, yay! These are the columns of the identity matrix. Beautiful. So, for example, the standard basis elements of R3 are as follows. So note the index is telling you where the 1 is in the vector. Cool. Alright, so I claim we're going to combine this with the power of this to prove matrix multiplication is associative. Alright, so let's see how that's going to happen. So the first thing we're going to prove is that I can now take a matrix and multiply it by an element of Rn. What happens when I multiply by a center basis element? You get the kth column. Beautiful. And let's see the proof of that. So note, again, the standard basis elements are defined to be the following. Their entries are 0 when these are unequal, but 1 when they are equal. So when I look at the jth entry of A times EK, so jth row of A is fixed, you let the columns run from 1 to n, and then you let this run there. So note, like again, we're doing a dot product. So specifically, you're doing the dot product of the jth row of A with this vector right here. Alright, so we do that summation, and hey, note, the standard basis element, there are a bunch of zeros. So almost every single term here dies except for 1, where it's equal to 1. So this is a very thematic move for us. We will see this happen repeatedly in the class, where you have a sigma, you've got a summation of some shit, and I don't want to deal with sigmas. So let me plug in something so that everything is 0 except for one thing. So everything deletes except for 1. We'll be doing this very frequently, so keep your eyes peeled. Keep your eyeballs out for that one, because oh boy, are we going to do this quite a bit. All right, but yeah, so in the summation, everything but one term is 0, and the term that's not 0 is AK, which is the jth entry of the kth column. So this element of Rm and this element of Rm have the same entries, so they're the same thing. Cool. So multiplying a matrix by a standard basis element gets you the column. And if the part of your brain is going, oh, can I multiply and get the row? Hold on to that thought. All right, so let's now prove that cancellation is not possible for matrix multiplication, but if you're talking about multiplying elements of multiplying a matrix by elements of Rn, turns out you can kind of get cancellation. So specifically, if I have two matrices, and I know that multiplying them by the standard basis elements, Rn, so note for the columns, if I know all of those line up, then I know the matrices are the same. And from the previous proof, that it hopefully isn't shocking, because these are the columns. I'm telling you the columns of the matrices are the same. They're the same matrix. But here's the gory details of that proof, if you're so interested. Beautiful. So here we see that we don't exactly have cancellation for matrix multiplication, but if I look at matrices multiplying by elements of Rn, I can kind of get cancellation. And in fact, as we're going to see, this is actually a special case of a much more powerful result. So keep that in mind as we go forward. All right, beautiful. So, okay, we've got a little bit of a sampling of taking a matrix and multiplying it by a vector and seeing the standard basis element in action. Let's take that a step further. Now, something the standard basis elements do is that they allow us to write any vector as a summation. Specifically, every vector can be written as a summation of scaled standard basis elements. And again, this is just invoking the fact that if I look at the kth entry of the jth standard basis element, the kth entry is 0 when k is not equal to j, and it's equal to 1 when k is j. So if I look at the kth entry of this summation, all right, well, that's what it looks like, and everything is 0 except for one thing, which is xk. That's it. Okay, and now with this result in hand, let's note that, hey, multiplying a matrix by standard basis elements gives you the column. So, if I take a matrix and multiply it by an element of Rn, it's actually just a summation of the scaled columns of the matrix. So you take the columns, you scale them by the entries of x, and then you add them up. That's an interesting way of thinking of it, right? So rather than thinking of it as the rows of A being dot product with X, we can instead think of it as the columns of A being scaled and added together. So there's two different ways of looking at A times X, a row way and a column way. Oh, that's really interesting and incredibly powerful. Okay, and from the previous proposition, we have this, and also from a previous proposition, multiplying this by A. So note, matrix multiplication distributes across addition, and you can pull scalars out. So the proof's over. Yay! See here. It's beautiful. Cool. All right. So let's ground ourselves again. What's our goal right now? Our goal is to prove the matrix multiplication is associative. And we're getting close. We're getting the ingredients. So note, everything we're doing right now is kind of experimenting and playing and investigating how multiplying matrices works. And we're seeing that there's a lot of facts about the rows and the columns that we can exploit. Right, there's a lot of trickery that can be done there. So let's keep going down that rabbit hole, and let's now prove that the kth column of a product of two matrices is the matrix A times the kth column of B. So when I do A times B and I look at its kth column, that's actually a matrix times a very specific vector. So this gives us yet another way of looking at matrix multiplication, so sort of a column way of looking at it. And here the proof is, again, just a simple unraveling of definitions. What is the jth entry of the kth column? Well, it's the jkth entry of the product. That's equal to this. And then if we look at this right here, we know that that's the h entry of the kth column. And this is, by construction, the definition of matrix times vector. So, the jth entry of that, as we've seen. All right, cool. Okay, so this reveals that the kth column of a product is the product of A with the kth column of B. So note, this is a sort of, you can move parentheses in a very specific way, which is exactly what associativity says, that you can move parentheses wherever you want. Ah, baby steps. So the next baby step. If I have a matrix B and I multiply it by an element of X, multiplying it by a matrix A is the same thing as multiplying the matrix A and B first and then multiplying X. So hey, you can move parentheses around. Cool. Right, and then keep track of all the dimensions here too. A times B is an element of Mn, so multiplying by an element of Rn gives you an element of Rm. X is an element of Rn, times B is an element of Rp, A is an element of MP, times Rp gives us an element of Rm. So these two things do live in the same set, so there is hope of them being equal. Alright, and indeed, if we write it out, recall that B times X gives you the sum of the columns of B scaled by the entries of X. Matrix multiplication is distributive, so the A's distribute. And, oh, hey, look, A times the columns of B. As we just proved, those are the columns of A times B. And, oh, hey, wouldn't you know it, that's by definition what this matrix times X is, as we proved. All right, it is the columns of the matrix scaled by the entries of X added up. Interesting. Neat little proof. So I'm allowed to move those parentheses around. All right, so here we go. We are now able to full out prove matrix multiplication is finally associative. And it only took us, like, what, 6 slides? Not that bad. All right, well, let's prove that A times B times C is a meaningful quantity. All right, and the trick is going to use the standard basis elements. All right, so I'm going to prove these two matrices are equal by showing that if I multiply them by standard basis elements, then they must be equal, which means the original matrices line up. And this is literally just parentheses the proof. Right, which shouldn't be too shocking. We're trying to prove that parentheses work the way you want them to, and yeah. But let's follow the logic. Let's follow each step to see that this is all good. Okay, so here I've got matrix times standard basis element. So as we proved, if you've got matrix times standard times a vector, I can move these parentheses inside here, which is what I just did. Okay, then I can apply that logic again, matrix times vector. I can move the parentheses over to have matrix times vector. All right, now let's look at what I got here. This is a vector times a matrix on the outside. So I can pull those parentheses out and have this matrix times this vector. So now I'm viewing this as a vector. This is an element, specifically, this is an element of RQ. Okay, and then now what do we have? Matrix times vector, and I know I can pull those parentheses over, and hey, A times B times C, A times B times C, when you multiply by the standard basis elements, they line up, so those matrices must be equal, and boom, there we go. We have proven matrix multiplication is associative, and it wasn't completely a nightmare. It wasn't an index nightmare, it was just a parentheses nightmare. So, not too bad. But, there we go. So, there we go. Here is a proof of matrix multiplication being associative, and as far as I can tell, this is somewhat original. Like I was saying, when I was looking around for a proof of matrix multiplication being associative, I was shocked and like, oh wow, this index thing, it's like impossible to actually get that to work. Even if you're really good with sigma notation, it's not an easy task to make it work with the indices. So, and when I was looking around, I was really shocked that you really can't find a good proof of it. And you know, I forget exactly how I got the idea for this. I think I was just playing around with the fact, okay, well, what happens if I multiply these by standard basis elements? Because if you're trying to prove the two matrices are equal, a lot of the times what you do is multiply them by standard basis elements and see if they line up. And then from there, I think I was able to put it all together. But, yeah, I have not seen this proof in this format the way I've written it anywhere else. So, might be somewhat original. We'll see. But anyway, beautiful. There we go. All right. So let's wrap up this party here. So we've now proven that matrix multiplication, while it has its quirks, is nice in a lot of respects. It has distributivity, it has associativity, it has identities. So it's it's not it's terrible just yet. And because it has identities, it could have inverses. So we'll get to that later. All right. But for now, let's wrap things up by looking at how matrix multiplication interacts with the other matrix operations we introduced. So we've already seen matrix multiplication interacting with scaling and adding. How does it interact with transposing? Well, it turns out that the transpose of the product is the product of the transposes in reverse order, and hopefully that is clear that that would have to be the case because of dimensions. So think about A times B. Transposing it, A times B here would be an M by P matrix. Its transpose would be P by M. So A transpose would be an N by M matrix, and B transpose is a P by N. So I can't do A transpose times B transpose. The dimensions may not line up. I have to do B transpose times A transpose. And if we work out the details of the proof, right, we see this happening. Look at the JKF entry, you transpose it. Proper transpose symbol, at least in this slide, screwed that up on the last one. All right, you swap it, you get JK. So you look in here, you swap them again. Matrix multiplication, real number multiplication is commutative, so I can swap them like that. And then the B turns into a C for some crackhead reason here. Oh, I had it as C originally, and then I changed it to B for reasons beyond my understanding. I think I had the A. I think I had it as a C at one point, so you can have a cat like C A transpose. Whatever, wasn't worth it. It never is. All right, so this is a neat little fact, and again, as neat little facts go, this will be one that will be appearing. So that's neat that matrix multiplication and transposing interact in a very nice way. All right, let's now look at trace and matrix multiplication. And so it turns out that even though A times B and B times A may be different, the trace of A times B and the trace of B times A are always the same. Woo. And it's not too difficult to see this, because if you write out what it is, summation of the KKF entry here, you get this. Summation of the JHF entry, you get this. Now, if you look at it, you'll see, oh, hey, AJK, AJK, BJK, BJK. The only difference between these two quantities right now is, oh, the summation starts with J on the inside and has K on the outside. Well, good thing matrix multiplication is commutative, so you can swap the order. Good thing that no, it's not. Good thing addition and multiplication of real numbers is commutative, so you can go ahead and swap the sigmas and get that the trace of A times B is the trace of B times A. Cool. So here's another sigma maneuver for you, being able to swap the order in which we do the additions. That is a completely legal maneuver. Beautiful. All right, so now that we have this in hand, we can actually prove one of my favorite results in matrix theory. Take two square matrices. A times B minus B times A never equals the identity matrix. Now, right now, you might be going, why would that ever hold? Why would you even think that A times B minus B times A is the identity? Like, why would you even give a shit? That's like a weird statement. We're going to be able to, you can prove this, but it might be like well, why would you even think that that would be true? Well, it turns out that, in my very limited understanding of quantum physics, you can view the statement A times B minus B times A equaling the identity matrix, basically saying that, okay, if you observe A times B, and then you observe B times A, so if you change the way you observed a event from happening, you don't expect them to be equal, so you don't expect their difference to be equal to 0. However, what you would like to be true is that even though you observe them in a different order, they're not too far away from each other, and their difference being the identity matrix would be nice. So it turns out that in quantum physics, you want A times B minus B times A to actually equal the identity matrix, but it literally cannot be true. So, and it's super slick proof for this. Suppose it was true. The trace of AB minus BA is the trace of the identity, which is equal to n, as we proved. However, as we just verified, trace respects scaling and adding, so the trace of a difference is the difference of the traces. And hey, A times B and B times A have the same trace, that's equal to 0. So from a quantum physics standpoint, you want this to be true, but it's just not so. So it's really interesting. I forgot where I saw this, where somebody was ranting about this. I think one of my upper level functional graduate books, somebody pointed this out, and I looked into it, and I was like, whoa, that's nuts. So, a fun little fact, A times B minus B times A can never equal the identity matrix. It seems at first glance like, yeah, why would you even think it, but we can prove it, so there you go. Alright. So there we go. We've now got a couple of results on how matrix multiplication interacts with our other favorite maneuvers on matrices, transposing and traces. So the last thing I want to talk about is powers of matrices. So multiplying a matrix by itself multiple times. So it turns out the basic facts about powers and powers works. So a matrix, so if you do a matrix to a power times matrix to a power, you get matrix times the sum of the powers. Matrix to power is matrix to the product of the powers. So we could talk about matrices squared, we could talk about matrices cubed, and raising matrices to certain powers behaves in manners that you would expect. And it turns out that there's some interesting things about powers and matrices. So naturally, hopefully your brain is going to, oh, hey, in the real numbers, given any non-negative real number, I can always find a number that squares to it. So square roots exist. Ooh, I wonder if some absolute bastard is going to subject you to matrix square roots. Ooh. On like a quiz or something, that'd be really bad. It would, Otherberry. Alright, so matrix multiplication, powers of it is defined recursively, so the 0th power is taken to be the identity matrix. That hopefully makes sense, as I already ranted, anything to the 0 power is equal to 1, and in this case, matrix multiplication R1 is the identity matrix. And then the powers are defined recursively as the a to the n plus 1 power is a to the n times a. So let us quickly point out that a to the 1, which would be a to the 0 plus 1, is a to the 0 times a. The identity matrix is a0, so the identity matrix times any matrix, as we pointed out, didn't prove, but pointed out, that gives you the original matrix. And likewise, squaring a matrix gets you what you think it should, a times a. And there it is in full detail. Alright, so now we're going to prove 3 and we're going to prove 4, and very similar to a proof that we did early in the class, we're going to do these by induction. Okay. So I claim a to the p plus q is equal to a to the p times a to the q, so we'll set up the set of all k that have that property, verify that the set is all of the natural numbers, including 0, and so the desired result follows. So I'm going to do my version of induction here. Okay, so first we'll note the initial element is in the set. If you plug in 0 here, it all works out. And so 0 is in the set. So now suppose we have k in the set, we'll prove that k plus 1 is in there. It starts at 0. Given any k, you can always add 1. So that means we've got 0, we've got 1, we've got 2, we've got 3, we've got them all. Alright, so let's replace this with k plus 1. We can move the parentheses over. Okay, by the recursive definition of powers, I know this breaks up into this. Here, I know this now, because k is in the set, splits up like that. Matrix multiplication is associative, so this is a meaningful statement right here. Good thing I proved that, otherwise I'd be in trouble. And we know what this is equal to by the recursive definition, it's that, so k plus 1 is in the set. Proof is over, e is all of the natural numbers including 0, so we're good. And there we go, proof by induction, and again, induction, the way I like writing it. You, of course, can write it however you want, but I like setting up a set and then demonstrating that that set behaves the way it should, right? Sets are the foundation that we use for mathematics, so I like to use them whenever I can. Alright, and finally, let's prove this, and this will be another proof by induction. So again, we'll do that. So first thing we'll note, replace k with 0 and show that k of 0 is actually in the set, and it's not too hard to see that that is true. You raise this to 0th power, you get the identity matrix, which is a to the 0, and 0 times anything gives you 0. Cool. So actually, it's worth kind of pausing it for a moment and realizing that each one of those steps required you to really think about something, right? We've defined 0th powers to get us the identity, and 0 times anything gives you 0. We're explicitly using a fact. Good thing we proved that that's true, by the way. Alright, so 0 is in the set, so suppose k is in the set. Let's show that k plus 1 works, so look at k plus 1. Alright, by the recursive definition, we know this is this matrix to the k times the original matrix. Since k is an E, we know we can pull this in, and then now by the previous point, matrix to power times matrix to power, we can add them up. And hey, I can factor. I can distribute. So k plus 1 is in the set, and the proof is over. Hey, good thing I know that addition and multiplication distribute. Beautiful. Cool. All right. So powers of matrices work basically how you want them. You want them to, as long as you're talking positive powers. When you get into negative powers, it's possible, but can't really talk about that right now. And it is possible to do fractional powers. It's possible to talk about the square root of a matrix in very specific situations. So I'll leave it at that. And I'll leave the video now. Beautiful. So there we go. We are now leaving chapter 1, and we'll head over into chapter 2, and we'll officially solve systems of linear equations. And as you're going to see, good thing we spent a lot of time building this stuff up, because now I've got a lot of machinery to make solving systems a little bit easier. Beautiful. Alright, so when I see you in person, that's what we'll talk about next time. But for now, we're done. See you later. Hope you liked it.